Hi, my name's Michael Lee. This is a talk entitled Adaptive Design Optimization for the Mnemonic Similarity Task and is a presentation for Virtual Math Site ICCM 2021. I'd like to start by introducing my collaborators. Most of the work I'm presenting was done by my graduate student Manuel Villarreal, and we collaborated with Craig and Shauna Stark. Craig and Shauna are experts in the mnemonic similarity task, which is a modified form of a recognition memory task. It involves an encoding or a study phase in which participants see 128 pictures of items, as we see here, and then a testing phase in which 64 of those items are represented as repetitions to be identified as old stimuli. There are 64 completely new stimuli, and there are 64 similar lure stimuli. And it's really those similar lures that make the mnemonic similarity task different. In between the old items that are exactly the same and should be identified as such, and the new items, which are brand new stimuli, are a set of lures ranging from fairly easy lures, which are the same objects but in very different visual presentations, down to very difficult lures that are hard to discriminate and so place strong demands upon pattern separation. The introduction of those lures is thought to make the mnemonic similarity task highly sensitive and reliable, and therefore a valuable tool, especially in clinical settings or in neuropsychological settings for identifying hippocampal dysfunction. As for any clinical test, however, it's important that the mnemonic similarity task be administered as efficiently as possible so that we can measure things as precisely as possible with as few trials as possible. And so our goal in this talk is to apply adaptive design optimization methods to the mnemonic similarity task to see if we can improve its performance. The data we use in this talk come from a 2015 study and involve 40 participants, half of whom were young, around about 20 years of age, and half of whom were elderly, around about 80 years of age, and they did the standard mnemonic similarity task that we've just described. This graph summarizes the basic properties of the data, showing the proportion of new responses ranging all the way from old stimuli up to new stimuli through those various stages of lures. We can see that there is a differentiation of the performance of young people who tend to do better and elderly people who tend to do worse. And notice also that if we had only done a standard recognition memory task with just old stimuli and new stimuli, we probably would not have been able to distinguish between the patterns of recognition of the young and the elderly participants. Adaptive design optimization requires a cognitive model, and we use an extended form of signal detection theory. We implement this in a slightly unusual way, treating the old stimuli as noise with a d prime of 0 and the new stimuli as signals with various levels of strength through the lures ranging up to completely new. So now responses to the right are correct rejections if they come from the new stimuli, or misses if they come from the old stimuli, and responses to the left are false alarms and hits. We implement this signal detection theory model as a Bayesian graphical model in JAX, and here's the graphical model that spells out the details of the modeling assumptions. The two important points are that both the D primes for the various lures and new stimuli and the old stimuli are modeled hierarchically, as is the criterion value across participants. So every individual has their own set of D primes and criteria, but these come from group distributions with means and standard deviations. And the second assumption we make is that there's the possibility that any trial can be a contaminant trial, and we do that with a latent mixture component, with some small base rate probability that any trial could be a contaminant trial corresponding to chance performance. When we apply this model to the data, we get sensible inferences. So here are the posterior distributions of the means for the criteria for both young and elderly participants, and for the various lures and for the new stimuli. In adaptive design optimization, the goal is to choose the next stimulus to be presented so that it's maximally informative about what we want to know. And what we want to know here are those group means for the criterion, for the old, the lure, and the new stimuli, and we place order constraints as per that signal detection theory model with the old distribution at 0, and then successively greater d primes as stimuli become more different from the one that was studied. And so at any point, according to the signal detection theory model, there'll be a posterior distribution for those news that we want to know based upon the behavioral data that have been seen to the teeth trial. And then the key question asked by adaptive design optimization is, what stimulus should we present next on the T+1th trial? Suppose we presented a stimulus that was from the Lua2 category. Then there are two possibilities. One is that the person responds new to that stimulus, in which case we would update our understanding of mu based upon this additional piece of behavioral evidence. And the alternative is that they could decide old to the Lua2 stimulus we've just presented them with, which would result in a different updating of the mu vector that we want to understand. And so it's natural then to measure how much information we gained from presenting that Lua2 stimulus on the T+1th trial using Kullback-Leibler divergence. Suppose they said mu, then we would have this posterior distribution having presented that stimulus, and we could compare its distance to what we had before based upon just the first T trials. And similarly, if they've said old, we would have a different level of information gained as measured by Kullback-Leibler divergence. We just note here that we use an approximation to measure Kullback-Leibler divergence, treating that joint posterior distribution over the mu parameters as a multivariate Gaussian, and this has a nice closed form that allows for efficient computation. But the key thing that we need to understand is, what's the probability of each of those possibilities? What's the probability that they will say old or mu? Because that will determine how much information we expect to gain. Well, the model tells us this. This is what the cognitive model is useful for. It's really the posterior prediction of the model says, what's the probability of an old or a new response on the T+1th trial, given everything that's gone before? And that's an integral across the model according to the inferred parameters of the model at that point. And so this provides the key bit of information we need to weight those two possibilities. And so our final expected level of information gained from presenting that Lua2 stimulus on the T+1th trial is a weighted sum of the two possibilities. And so this provides how much information we would expect to get if we presented Lua2. And the final step is just to say we want to now maximize which stimulus we actually present to be the thing that maximizes the expected information gain over all of the stimulus types that are available to us. We tested this adaptive design optimization method against our data by having it reorder the 192 trials that each participant did, generating a hypothetical order in which they would have encountered those trials if adaptive design optimization had been applied in their experimental setting. Notice that this means that adaptive design optimization will end up in the same place as the original experiment, because both in the end will have seen the same 192 trials, but we're interested in whether the order that adaptive design optimization comes up with enables us more quickly to get good inferences about what will eventually be the inference once all of the data have been seen. To measure the performance of adaptive design optimization in this testing scheme, we again use the Kullback-Leibler divergence, but now to measure the difference between the final posterior distribution that will be achieved when all the data have been seen, mu star, and the posterior on mu that is currently available through either adaptive design optimization ordering or the experimental ordering that the participants actually did. Here are some results for one individual young participant. The Kullback-Leibler divergence is summarized down here across the 192 trials, and you can see that it falls slightly more quickly under adaptive design optimization. This dotted line shows the first point at which a stimulus wasn't available that adaptive design optimization wanted, and you can see at that point it's outperforming the experimental order. The other panels show specific elements of the model, the criterion or the D primes associated with the lures or the new stimuli, and show in the yellow the experimental inference about the posterior distribution for that parameter, and in the blue the adaptive design optimization inference. And so we can see in this example, the reason adaptive design optimization performs better is that it's more quickly able to learn about the final posterior D prime for the Lua4 stimuli. Eventually, This is what both models will converge to because that's the inference about that D prime when all of the data have been seen. And you can see that adaptive design optimization gets there after about 30 trials or so, whereas the original experimental order had considerably more uncertainty for a large number of trials. Here's another example, this time involving an elderly participant. We can see that again, adaptive design optimization outperforms the experimental order. And if we look at the specific parameters, we can see that the main cause here is in Lua 5, which again, the adaptive design optimization managed to learn about more quickly through the order in which it presented stimuli. Here's that graph of summary performance for all 20 of the young participants. We can see that adaptive design optimization usually outperforms the experimental order, sometimes by a lot, often only by a little and early on in the trial sequence, and there are some exceptions, but overall adaptive design optimization does lead to some improvement. Here are the same patterns of results for the elderly participants, and we see the same sorts of features. Adaptive design optimization is generally better, often by a lot, sometimes only by a little, and there is the occasional exception. One interesting analysis to understand the performance of adaptive design optimization is to look at when it drew upon stimuli from each of those different stimulus types. That's shown in these graphs. So for example, in this panel, we have the pattern with which the Lua 4 stimuli were presented. And you can see for adaptive design optimization, it presented the first one here and then presented many Lua 4 stimuli in a row. It prioritized the presentation of these. The dots indicate that it was the highest expected information gain stimulus at that point. And you can see that it presented them much earlier than the random experimental order did. This is for that participant we showed earlier where the ability to identify more quickly the posterior distribution of the Lua 4 discriminability was the important part in improving the inference. And you can see how design optimization has achieved that here. Notice that adaptive design optimization almost certainly could have done better here if it had had more Lua 4 stimuli available. After it had presented all of the ones that were available, it often had as its highest priority presenting another one that wasn't able to do it. And so this would suggest a better assessment of this individual could have been done if instead of a whole bucket of new stimuli being available, there had been many more Lua 4s and Lua 5s and Lua 1s, for example. Despite those promising results, it's always possible to do better, and there are two main ways in which we could look to improve the performance of adaptive design optimization further. One is through improving the cognitive model. It's generally the case that the better the underlying cognitive model, the better adaptive design optimization will perform because those predictions about future behavior become better. In fact, we've already done some of this. The contaminant component that we introduced to the model was critical in the success that we've demonstrated. Without that, adaptive design optimization really didn't improve upon the experimental order. But of course, we could go further. And in particular, thinking about some sort of learning or sequential effect seems important in this sequential testing task. Second way would be to improve adaptive design optimization itself, or at least extend it. We're currently only doing one trial ahead, greedy optimization, thinking about the next stimulus to be presented, but we could look to optimize further ahead than that. But also think about whether expected information gain is always the right thing to optimize over. It might be that something like maximizing the worst case information gain, sort of minimizing the possibility that you'll really learn nothing, is a good way to choose the next stimulus. It might be more robust or more effective in some sense. It probably depends also upon exactly what the goals of the measurement are. The obvious next step is to test adaptive design optimization in experiments where there are not any limits on the availability of each stimulus time. Assuming that that works well, there would still be some work to do to realize the potential of adaptive design optimization in a practical setting. So we may need to work on some point estimate approximations using the current full implementation as a benchmark and test its ability to realize benefits in terms of how quickly and efficiently you can measure people's recognition memory. And then finally, we're interested in extending these basic ideas to other versions of the mnemonic similarity task, in particular a continuous version that doesn't need time-consuming training sets, just presents sequences of stimuli and asks people whether those have been studied as part of this sequence before, that will require a more extended cognitive model that will involve a more detailed account of learning than our simple signal detection theory model applies, but would be an interesting application of adaptive design optimization methods.